Welcome back to A Slice of Physics. I'm sure you've heard of Newton's three laws of motion. In this course, we're going to spend most of our time working with various aspects of these laws. So let's begin with reviewing what you already know about these laws and building a deeper understanding. We'll start with Newton's first law of motion, which has to do with a property of matter called inertia, which deals with the natural state of objects. Let's start our discussion about the natural state of objects by going back to Aristotle's time. Aristotle was a Greek philosopher who lived in the 4th century BC, and he thought about a lot of things, and based on his thoughts, he formulated a number of laws. One of them had to do with the natural state of objects. Perhaps based on his day-to-day experience, Aristotle believed that objects tend to remain at rest, or tend to come to a rest, on their own accord, and in order to keep them moving, we must apply a force. After all, this is what we see around us all the time. For example, if I have a box here on the floor, and I give that box a firm push to the right, it's going to slide for a little while, and then it'll come to a stop, perhaps here. The same is true with a car. If you're driving your car on a straight highway, in order to keep it moving, you need to keep the gas pedal pressed here. And if you take your foot off the gas pedal, the car will roll for some time and eventually come to a stop, perhaps at this point. So when we think about the box here or the car here, they both seem to come to a stop on their own accord. But on the other hand, in order to keep them moving, you got to apply a force continuously on the box or on the car. So our common sense, which is based on our day-to-day understanding such as these, seems to agree with Aristotle. Now, about 2,000 years after Aristotle, another scientist was thinking about these things, and his name was Galileo Galilei. Galileo is regarded as the first true scientist by many people because he based his conclusions on observations and experiments, which tested his hypotheses. So Galileo thought about the same things Aristotle was thinking about, but just a little more deeply. So for example, in the motion of the box we had, let's take the example of a wooden box on a wooden floor, and let's just say the box's surface and the wooden floor surface is fairly rough. So this box, if I give it a firm push like I did before, it's going to slide a little bit, and then it's going to come to a stop maybe here, just like Aristotle saw and all of us have seen through the ages. Now here's where Galileo took it further. So if we now imagine the same wooden box, just with a smoother surface on a smooth marble floor, and I give it the same push, what would we expect? Well, common sense will tell you that because the floor is smoother, the box is going to slide farther before it comes to a stop, perhaps over here. And if I have even smoother surfaces, so let's say I have an ice floor and I have a block that's the same size and shape as a wooden block here that's made of ice, and I give it the exact same push, it's going to slide even more. You know that ice sliding on ice, there's not a lot of braking effect, so it's going to slide a lot farther and perhaps go here before it stops. So what's happening that causes the change in this behavior? Well, the roughness of the surfaces or the smoothness of the surfaces impacts the motion. And the rougher the surface is, the box stops sooner because the braking effect is stronger. And the smoother the surface is, the box slides a lot more because the braking effect is not as strong. All of these observations fit our common sense as well. Now here's where Galileo's insight took this to a whole new level that gave us a deeper understanding and a more correct understanding of the natural state of objects. If we were to imagine an infinitely smooth surface, I'm going to show it here and call it infinitely smooth, and place a box on it that also has an infinitely smooth surface and give it that same push, how far is it going to go? Well, Galileo concluded that in the absence of friction, which is an external force that produces a braking effect on the motion of these objects, in the absence of that, this box is going to keep moving forever in a straight line. So when it gets here, it's still moving in the same direction with the same speed. When it gets here, it's still moving in the same direction with the same speed, and so on forever and ever and ever. This was Galileo's insight. And this property for an object to keep doing what it's doing unless an external force acts on it is called inertia. So the object does not want to change its state of motion. So here, let's take another example, and let's let the box just sit there. So it's just sitting in this spot, and we all know from common sense that unless we apply a force on it, it's going to keep sitting. Here, we had to push these boxes to get them to start moving. So if we don't push, this one's going to keep sitting in the same spot and not change anything. And from Galileo's insight that we have just now discussed, if the box is moving already, in the absence of any external force, the box is going to keep doing what it's doing and not change its state of motion. And that's the natural state of objects. Not to come to a rest, but rather to keep doing what it's doing. So that brings us to Newton's first law of motion. You might have been wondering that we started talking about Newton's first law of motion, and so far we've discussed Aristotle and we've discussed Galileo, but we haven't come to Newton yet. Well, Newton did a great job of codifying a lot of what was known before him and then building on it. And he himself said that if people think I've accomplished a lot, it's because I have been standing on the shoulder of giants. And one of the giants' shoulders that he stood on was certainly Galileo. So Newton's first law of motion has to do with objects which have no forces acting on them. And for these objects, Newton's first law says that if they are at rest, they will remain so. And if they are moving, they will continue moving in a straight line at the same speed. So it essentially restates what we have discussed as inertia. Let's talk about these in terms of some of the physics terms we have been using. So essentially what Newton's first law says that if force is zero, then if at rest, meaning if velocity was also zero, velocity will continue to be zero. And if velocity was not zero, which means it was moving, velocity again remains unchanged. And we know that the change in velocity is called acceleration. So in equation form, we can simply write Newton's first law as if force is zero, then acceleration is zero, which means that if it was at rest, it remains at rest, and if it was moving, it continues moving in a straight line with no change in speed. So do we have any practical example that confirms Newton's first law? Well, we launched two spacecrafts in 1977 that were called Voyager 1 and Voyager 2. Well, these spacecraft have now traveled farther than all the planets in the solar system, and by some measures have exited the solar system. So what are they doing now? Well, they are traveling at a speed of 40,000 miles per hour in a straight line. So they're speeding through space faster than a bullet. And why are they doing this when they have run out of propulsion fuel? Simply because that's all they have been doing. And far away from all of the other objects and far away from any material that will cause any friction or drag, they really don't have any external forces acting on them to speak of. So they're simply following Newton's first law and keeping an unchanged velocity. So to recap, we have discussed Newton's first law of motion in this video that deals with the property of inertia, which is the natural state of objects, and simply states that if no force is applied on an object, the object maintains its state of motion or non-motion, which is to say that if it's at rest, it remains at rest, and if it's moving, it continues moving in a straight line with the same speed. In equation form, it simply says that if force is zero, then acceleration is zero.